I'll briefly demonstrate how to use an interactive simulation that shows the dependence of fugacity on temperature for ideal binary mixture, in this case, benzene and toluene. And so this is a system that obeys Raoult's law. The simulation is located on the LearnChemE website. Here's the link. And then here's a snapshot of what the simulation looks like. Fugacity versus temperature. At the low temperature, we have liquid, and so fugacity is proportional to the mole fraction times the saturation pressure. Saturation pressure is increasing exponentially with temperature, and so the fugacity is increasing exponentially. At the high temperature, we have gas phase. Now the fugacity doesn't change with temperature because fugacity for an ideal gas is the same as the partial pressure. Partial pressure is not changing. Total system's at constant pressure, therefore the partial pressures aren't changing because the mole fractions are not changing. And so if the overall mole fraction 0.6 for benzene and we're at 1 bar pressure, then the fugacity is 0.6 bar in the gas phase. In this region, a two-phase region, we see the fugacity of B is decreasing and the fugacity of toluene is increasing. Well, the reason it's decreasing will show more clearly when we look at the TXY diagram, but essentially the mole fraction of benzene in the gas phase is decreasing, and so the mole fraction, gas phase times the pressure is fugacity, and so therefore the fugacity is decreasing. So let's look at this simulation. And so the TXY diagram, if we start at low temperature and we increase the temperature, remember, we're increasing fugacity because we're increasing the saturation pressure. Now we hit the two-phase region. Here's the fugacity benzene. It's going to be the gas phase mole fraction times the pressure. So it's a high value, and as I keep raising the temperature and get more and more into the vapor phase, then the fugacity of benzene is decreasing, the fugacity of toluene is increasing. Well, we can look at both these diagrams together and look at how, as we change temperature, we see the changes in fugacity, and we can see how changing the mole fraction changes what these diagrams look like. So, understanding vapor-liquid equilibrium fugacity is important, particularly when we look at non-ideal systems, because fugacity is the driving force for mass transfer. Setting fugacities equals how we determine vapor-liquid equilibrium. Now, in these simulations, there are some directions, brief, and then there are details that have the equations that are used to generate the curves.